Okay. So before introducing public key crypto system or asymmetric key crypto system, we have to go through some basic number theory. You are most of you are familiar with most of the things that we are going to discuss here. So first, I will start with this division algorithm. It says that given any two integers with b greater or equal to 1, if you divide this a by b, you will get a unique quotient and a unique remainder, a equal to bq plus r. Okay, so where this r remainder is in between 0 and b. So this remainder can be 0, or if it is not 0, then it must be a positive integer and must be less than b, the divisor. Okay, so this r, we denote this r as a modulo b, q is a division b. This can be proved using the well ordering principle of positive integers. Okay, so we will not discuss that proof, but this is essentially the basis of number theory, you can say. Now, these are some notations. Already you are familiar with this. A division b, so this is the quotient, and the remainder we denote by a minus b times the quotient. Okay, so this quotient, this remainder r can be written as a minus b q. Q is a div b. This means this integer part. Okay, so this way you can write. This is essentially the quotient q, and this is the remainder. And the ceiling and floor functions, you already know these things. I will not discuss this. Common divisor and greatest common divisor. Essentially, this greatest common divisor plays an important role in designing certain crypto systems. Okay. So common divisor, you know, common divisor C is a common divisor means C divides A as well as C divides B, and greatest common divisor is the greatest value. Means if D is the greatest common divisor of A and B, means D divides A and D divides B. And if you take any other common divisor C that divides A and B, then D is the greatest one. This is greatest common divisor means that C must divide D. Okay, C must divide. So these two conditions. Greatest common D is greatest common divisor of A and B. If D is a common divisor of A and B, this is first condition, it must be a common divisor, and also it should be greatest. That means if you have another common divisor C that divides A and B both, then this C must divide D. D is the greatest common divisor. And convention is GCD of AB is the equivalently you can define in this way also. GCD of AB is the least positive integer, largest positive integer that divides both A and B, with the exception that GCD of 0, 0 is taken to be 0. Okay. Okay, so least common multiple, all these things you know. These are very basic things. I'm not going to discuss. And if a least common multiple of AB and greatest common divisor of AB, if you multiply them, then you get the multiplication of A and B. So these are basic elementary level maths. And relatively prime, when we say two integers are relatively prime, if they are relatively prime or co-prime, whenever their GCD is 1. So these terms we are going to use frequently in cryptography. Choose two integers which are co-prime or which are relatively prime. So we just go through these things once. Okay. And prime means, you know, this prime, I don't have to define that. So regarding these prime numbers and composite numbers, we have this Euclid's lemma. Euclid's lemma says that if P suppose P is a prime, P divides AB, then either P divides A or P divides B. Means this we know by heart, or maybe it divides both. So we know this by heart, but there is a proof of this. Means this is Euclid's lemma. How to prove that? Okay. So if you have done some number theory, then you must be familiar with this proof. I will not discuss this proofs. Okay. And it is not for P device AB. It can be extended, generalized also. P device A1, A2, the product of A1, A2, AL say, then P device either A1 or A2 or AL, or all of them, or combination. Okay. And Euclid's theorem, it says there is an infinite number of prime numbers. This also means can be proved. Means we are not going to discuss these proofs. I will just mention this here. Okay, prime numbers. We have infinite supply of prime numbers. Okay, so prime number theorem, it says maybe this one may be new for you. Prime number theorem, it says suppose you count the number of primes less or equal to x. In pi x, suppose pi x denote that number. Now pi x is the number of primes which are less or equal to x. Then this limit extends to infinity, pi x divided by x by ln x equal to 1. That means pi x is almost equal to x, can be approximated by x by ln x. So this is prime number theorem, means very popular theorem, and the proof is not straightforward. It was proved by Hadamard and Vallée-Poussin independently using Riemann's idea. So these are famous problems in number theory. So pi x can be approximated by x by ln x. So this fact essentially we are going to use. We are going to use in many places. In many places. So we have some other refined results. Phi x denote the number of primes less or equal to x. Then if you take x to be greater or equal to 17, then pi x is greater than x by ln x. And for x greater than 1, pi x is less than this factor into x by ln x. So pi x is not exactly equal to x by ln x. Sometimes it depends on the value of x. As x tends to infinity, this limit is approximately 1. And we have for some values of x, it is greater than x by ln x. For some values of x, it is less than this value. Okay, so this factor also very important, how to reduce this factor. And the fundamental theorem of arithmetic, this is essentially called the unique factorization theorem. It says that every integer n greater or equal to 2 has a prime factorization, unique prime factorization, unique up to the given ordering of these primes p1, p2, pk. So every integer has a factorization as a product of prime powers. N is can be written as p1 to the power e1, p2 to the power e2, pk to the power ek. p1, p2, pk, these are prime numbers. And yes, this p1, p2, pk are distinct. And ei's are positive integers. And furthermore, the factorization, this factorization is unique. Unique up to the rearrangement of the factors. Up to the rearrangement of the factors. If you fix the ordering p1 less than p2 less than pk, then it is unique in that sense. Okay. Now, these are all well-known things. I will not go through this. So, I'm interested in this Euler's phi function, Euler's Taussian function. It says this is denoted by phi n. So, phi n is the number of primes, number of integers less than n and co-prime to n. Okay, so you count all the numbers which are less than n and relatively prime to n. That number is phi n. Already we have used this. So there are several properties of this phi n, Euler's Taussian function. Essentially, when we will discuss RSA encryption scheme or RSA digital signature scheme, this phi n plays an important role. We will see that. Okay? So we are interested in the properties of this phi n. So Euler's phi function, it has the property, these three properties. If p is prime, then phi p is simply p minus 1. You must be knowing this thing. Okay, so let me just go through this once again, and we will also give the proof. Not immediately. After a few classes, I will discuss these proofs, give you some idea how to prove these things. Okay, so this one p is prime, then phi p is p minus 1. And Euler's phi function is multiplicative function. Multiplicative function means if you take m and n to be co-prime, then phi mn is the product of phi m and phi n. Okay, so so number of this essentially counts number of primes which are number this essentially counts number of integers which are less than mn and co-prime to mn. This is essentially same as number of integers less than m co-prime to m as into number of integers less than n co-prime to n. Okay, this can be proved. This we are going to show how to prove this. Okay? And the more general one is if n has this prime factorization, then phi n we have this formula for phi n. If you know the prime factorization of n, then you can calculate this phi n. Okay, so this is essentially n into 1 minus 1 by p1, 1 minus 1 by p2, 1 minus 1 by pk. p1, p2, pk are distinct primes, distinct primes appearing in n. Okay, so this results we are going to prove after a few classes maybe. And also we have an explicit lower bound on phi n. If n greater or equal to 5, then phi n is greater than n by 6 ln n. Okay, so next is some congruence relation. The integers modulo n. N is positive integers. Okay, already we have discussed this while introducing this classical ciphers. Let us go through this once again. The integers modulo n is any positive integer. If a and b two integers, then a is said to be congruent to b modulo n. We write it as a congruent to b modulo n if n divides a minus b. N divides the difference of a minus b. Okay, so it can be written as a minus b is congruent to 0 modulo n. That means when you divide a minus b by n, it will give you 0. That means n divides a minus b. The integer n is called modulus of the congruence. So this is modulus of the congruence. Properties of congruences, you can prove all these things. Take these proofs as exercise. Okay. So I think means this proof I am going to discuss. That's why I write here proof. Okay, the proofs that we are going to discuss is written here in short. So this one I will not prove. You can go through this. These are very trivial things. You can always prove this. If you remember this definition, you can prove all these things. Okay. So a congruent to b modulo n means when you divide a by n, whatever remainder you get, dividing b by n will also leave the same remainder. Okay. So a congruent to b modulo n if and only if a and b leave the same remainder when divided by n. Okay. Reflexivity, a is congruent to a modulo n. Symmetry, if a is congruent to b modulo n, then b is congruent to a modulo n. And transitivity, a congruent to b modulo n, b congruent to c modulo n, then a is congruent to c modulo n. Transitivity property. And a congruent to a1 modulo n, b congruent to b1 modulo n, then a plus b is congruent to a1 plus b1 modulo n. And the multiplication ab is congruent to a1 b1 modulo n. Okay, so these things, this easy exercise, you can go through this and do it by your own. Now we are interested in Zn. Okay, Zn also plays an important role in designing crypto system. Okay, so integers modulo n. So all the integers modulo n it is Zn, the elements are modulo n means how many remainders you will have. So 0, 1 to n minus 1, this is the set Zn, set of all integers in this set. So addition, subtraction, multiplication in Zn are performed modulo n. Now this multiplicative inverse, formally I am now defining this. So already we have used this in, I think, in Virginia cipher. Somewhere I have used this. Okay, Miss affine cipher, I think in affine cipher we have used this, finding the modular inverse. So A belongs to Zn. A is an element modulo n. The multiplicative inverse modulo n is an integer x belongs to Zn such that Ax is congruent to 1 modulo n. Multiplicative inverse of A. Multiplicative inverse of A means A belongs to Zn. So multiplicative inverse of A modulo n will be also an element of Zn. So you have to find this x belongs to Zn such that when you multiply A and x, it gives you 1 modulo n. That means I can write it as A is x inverse or x is A inverse modulo n. So A is x is multiplicative inverse modulo n. Provided their multiplication gives you this one. It is congruent to 1 modulo n. Okay, so if such an x exists, it is unique and A is said to be invertible or a unit. Okay, so A is called unique. The inverse of A is denoted by A inverse. And A and B, A division A by B modulo n. Okay, these are trivial things. A and B belongs to Zn. Division of A by B modulo n is the product of A and B inverse modulo n. So A divided by B, when you write A divided by B modulo n, that means we mean to say A B inverse modulo n. It is not, suppose I am dividing 5 by 2 modulo 13, suppose. 5 by 2 modulo 13. So if you just say 5 by 2, whatever fraction you get, it should be performed modulo n. So A by B, that is 5 by 2, essentially same as 5 2 inverse modulo 13. Okay, so we are working modulo n. So all the operations are modulo n. Okay, so 5 by 2, if you write 5 by 2 is 2.5, it will not work. Okay, so you have to find 2 inverse modulo 13 and multiply it with 5. And is only is the product of A and B inverse modulo n and is only defined if B is invertible modulo n. Okay, B inverse modulo n exists. If B inverse n modulo exists, then only A over B, A divided by B modulo n exists. It is defined. And the fact A belongs to Zn, A is invertible if and only A and n are co-prime. And also this one I am going to prove. Okay, the congruence relation, this one I am going to prove. Suppose means this one says A is invertible if and only if GCD of an is 1. That means A is co-prime to n. Already this result we have used. In affine cipher, we have used this relation. That we have made a condition that if you take the affine transformation to be Ax plus B, then that A must be co-prime to 26. Means if we are working on Z26. Okay, so this condition is needed for the existence of inverse of A belongs to Z26. So if GCD of an is not 1, suppose it is D, and we are considering the congruence equation X congruent to B modulo n. Okay, so I am considering the congruence Ax congruent to B modulo n, where A and n, they are not co-prime. A and n, their GCD is D. Then this congruence, how many solutions we will have for X in Zn? In Zn, how many solutions we will have? This has a solution X if and only if this D divides B. This D divides B. So GCD of A and N is D. If D divides B, then it has a solution. And this is if and only condition. And how many solutions we will have? In case D divides B, we will have D many solutions. We will have D many solutions. Okay. So this congruence equation has no solution if D does not divide B. And in case D divides B, it has solution. And how many solutions it has? It has exactly D solutions. We are going to show this. Linear, how to solve linear congruence. This is a linear congruence. Okay, linear equation in X. Linear congruence equation in X. Linear congruence, how many solutions it will have? We are going to prove these things. And this result we will use in many crypto systems, in designing many crypto systems. Okay, so in case D divides B, it has exactly D solutions between 0 to n minus 1. Solution, whatever solution you will get, that should be in Zn, the solution modulo n. Okay, so it should be modulo n. That means the solution X will be between 0 to n minus 1. And how many solutions you will have? D many solutions that will satisfy this equation. D many X values you can get that satisfy this equation. Okay, these solutions are all congruent modulo n over D. All these solutions are congruent modulo n over D. And this D is the GCD. D divides D is GCD means D A and GCD of A and N means D divides A, D divides N. So D divides A, D divides N. Also solution exists means D divides B. The whole thing you divide, you can divide. So you get the equation A over Dn equal to congruent to B over D modulo n over D. You can that congruence, this congruence can be converted into that congruent, and that congruent is having a unique solution. Okay, from that you can get D many solutions of the original equation. We are going to prove that. How to get this, we will discuss that. So I have given here two exercises. How many solutions? Find the solutions of the following congruences. So whether first you have to check whether solution exists or not. Okay. So for the first example, you have to find the GCD of 123 and 456 and check whether the GCD divides 12 or not. So finding the GCD of 123 and 456, GCD of 123 and 456. So you have to find GCD of 123 and 456 and check whether that divides 12 or not. Okay. Similarly, here also you can rewrite this as 15x congruent to 20 minus 4 16 modulo 25, and now check whether 15, 25 congruent. I mean 15 and 25, their GCD is 5. 5 does not divide 16. This second equation does not have any solution. Okay, so you find, you do this exercise by your own. Okay, so this type of congruence, solving this type of congruence equations, I will ask you this type of problems. Some problems where you have to find the GCD of these and these, and so this consists of several problems. First, you have to find how to find the GCD. You already know that, but if these are very large numbers, how to do that in systematic way, and also how to solve that. What are the solutions? Here only I have mentioned that if D divides B, it has D many solutions between 0 and n minus 1. What are the solutions? Okay, so those. You have to know that thing to get the solution of that. I will discuss this. So this is the algorithm. Actually, I was talking about this one only. So you have the congruence X congruent to C modulo M, and D is the GCD of A and M. Okay, A and M, the modulus and this A. GCD is greater than 1, and also we are assuming D divides C. So this equation has solution, D many solution. So what are the solutions? So you recall that if D does not divide C, it does not have any solution. So what I will do, I will this congruence equation can be rewritten as, since D is the GCD of A over N, I can divide this whole equation throughout by D. Okay, it can be proved that this recurrence, this congruence and this congruence are same. So A over D x means this equation, I construct this equation, and solution I call the solution to be y. Okay, so from that y I will find the solution x for the original congruence. So instead of writing x here, this modified equation, the variable I take to be I take the variable here, instead of x I take it to be y. Okay, so now if you rewrite this way, then GCD of A over D and M over D, this is 1. So A over D and M over D, these are co-prime. So this co-prime means this is co-prime means it has a multiplicative inverse. This is co-prime. These are co-prime means it has multiplicative inverse. So you can find the multiplicative inverse of A over D modulo M over D. How to find the multiplicative inverse modulo something also, that is also we will discuss using extended Euclidean algorithm how to find the multiplicative inverse. So here we have seen that A belongs to Zn, A is invertible if and only if A and N are A and this modulus N are co-prime. So that we are using here. Since this reduced equation, now this modified congruence, for this modified congruence, we get A over D and M over D. These are co-prime. This GCD is 1. So A over D, this has multiplicative inverse modulo M over D. Multiplicative inverse modulo M over D. Okay, so that once you determine that inverse, you can simply multiply this with that inverse and you get the unique solution. So whenever A over D, M over D has are co-prime, then this equation has a unique solution. That unique solution we denote by y naught. So this is your first step. Okay, so given this equation, you convert it into this equation which has a unique solution y naught. This equation has a unique solution y naught, since GCD of A over D, M over D 1. Then the solution of the original congruence. So this equation has unique solution y naught. So then this equation will have solution. This y naught is also a solution of this, and the other d many solutions it has. So y0. Then y0 plus m over d, then y0 plus 2m over d, y0 plus d minus 1 m over d. Okay, these are the d solutions of the original congruence. So this is your algorithm to find the solution of this equation, this linear congruence equation. Okay, this is the solution. This is the solution. Why these are the solutions we will explain later. Okay. We'll again come to this. Okay. So applying this, you can now solve this problem. 2 and 10, GCD is 2. It does not divide 7, so no solution. Similarly, this you can check. Let me explain. I have done something here. 6 and 21, GCD is 3. 3 divides 12, so it has a solution. 3 divides 12, 6 and 21, their GCD is 3, and 3 divides this. So it has a solution. How many solutions it has? The GCD many number. That means three solutions it will have. So what I will do throughout this equation, I will divide by this GCD 3. So 6 by 3x, 12 by 3 mod 21 by 3. So I get this equation. This equation has unique solution. So we have to find 2 inverse modulo 7. 2 inverse modulo 7. So this modulus is very small. You can go for exhaustive search. Okay. So if the modulus is very large, then we have to apply extended Euclidean algorithm that we are going to discuss in within next few classes. Next classes I will discuss. So 2 inverse modulo 7 is you can calculate 2 inverse means 2 into 1, 2 into 2, 2 into 3, 2 into 4. When you get 2 into 4, 2 into 4 is 8 and modulo 7 gives you 1. So 2 into 4 is giving you 1 modulo 7. So 2 inverse is 4. So original solution, so this equation has unique solution. That is solution y0 will be 2 inverse into 4 modulo 7. 2 inverse is 4. So 2 inverse 4 modulo 7. That means 4 into 4, 16 modulo 7. That means 2 modulo 7. 16 modulo 7 means 2 modulo 7. 7 you divide 16 by 7. So 14 and the remainder. So 2 is the remainder. Okay, so the other solution, so first solution is y naught, that is 2. Then the next solution is 2 plus 2 plus m by d. M by d means this by d, that means 4, 7. Okay, 21 by 3. Then 2 into 21 by 3. 3 solutions. These are the 3 solutions. Okay, so the solutions are 2, 9 and 16. Okay, so when GCD and 2 and 7 1, you can so this is Bejout's identity. It says that GCD can be written as means if GCD of 2 and 7 is some D, then it can be written as 2u plus 7v. 2u plus 7v. Right, this is Bejout's identity. So by extended Euclidean algorithm, we can always find this u and v. Okay, so in case GCD is 1, you take modulo 7 here. If you take modulo 7, so we get this congruent 1 congruent to 2u and 7 modulo 7 means it is gone. So 1 is congruent to 2u modulo 7. So essentially 2 inverse is u modulo 7. 2 inverse is u modulo 7. So we have a mechanism to find this u and v using extended Euclidean algorithm. That means finding that this u is essentially the modular inverse of u, 2 modulo 7. So we can find, we will discuss extended Euclidean algorithm. Okay? Extended Euclidean algorithm. Means if you have this modulus very small, then by exhaustive search you can easily find the inverse like this. Okay, but if instead of 7, it is suppose a 4-digit number, suppose 7777. Modulo 2 inverse, modulo 7777. So how to find that? By exhaustive search means it is not feasible because 7777 is very large. So you have to have an efficient algorithm to find the modular inverse. So that is extended Euclidean algorithm. We will discuss this. Okay, so this type of problems I will ask. Okay. Some assignments I will give. Now this is another important theorem that we use several times in designing public key crypto systems. Suppose I have this system of linear congruence. Okay, it was one linear congruence equation, solving linear congruence equation. Now I have a system of linear congruence equation. So x is congruent to a1 modulo n1, x is congruent to a2 modulo n2, x is congruent to ak modulo nk. And this n1, n2, nk, they are mutually prime, mutually co-prime. That means if you take any two ni nj, ij from 1 to k, then their GCD is 1. So we have if the integers n1 into nk are pairwise relatively prime, then the system of simultaneous congruences, this has unique solution modulo the product of all these modulus. So this system has a unique solution modulo n equal to n1 into n2 into nk. The condition this system has, this n1 into nk, these modulus are pairwise relatively prime. Okay. So The explicit solution, it has unique solution, and what is the solution? It is given by the next algorithm, Gauss algorithm. X is the solution X to the simultaneous congruences. This is the simultaneous congruences. The solution A modulo n is given by this x equal to summation a1 ai ni mi modulo n, where ni is this ni is product of all these primes divided by small ni. So n1 is n2 into n3 into nk. N2 is capital N2 is n1, means all are product of all of them except the ith modulus. Okay, so ni is product of all these modulus except the ith term, and mi is that ni inverse modulo ni. Okay, mi inverse this mi is ni inverse modulo ni. Okay, so if you take x to be explicitly in this form, then you can show that this system, this x satisfy this system of equations. Each of these equation is satisfied by this. Okay, we will discuss that later. For the timing, let us learn how to apply this. So if you have if you are given a system of simultaneous linear equations with these conditions on the modulus, they are relatively pairwise co-prime, then you can find the solution of this system, solution modulo the product of all the primes. Okay, and this solution explicitly is given by this formula. So this x in constructing x, you know all the i's, so you can find ni also. This n is also known. N is the product of all primes, and ni is product of all primes except ni. And mi inverse also, by extended Euclidean algorithm, you can find mi equal to ni inverse modulo n. And this is polynomial in the size of the modulus n, size of this product of the modulus, product modulus n. The polynomial. So this size, if n is the given, n is the number, the modulus, then log n is size. So it is in the order in the polynomial in the size of the size of n. This bit operations. Okay. So essentially the this addition does not take much time, but the modular, you have to perform modular inverse operation. That actually takes log n square time. Okay. So one problem I have, very small problem I have taken. Okay, x is congruent to 3 modulo 7, x is congruent to 7 modulo 13, and we have to find the solution of this system modulo 7 into 13. Okay, so this has a unique solution modulo x equal to modulo 91. So how to find that? How to find that solution? So x will be x. This formula I am applying. This formula I am applying. So x will be a1 into these two product divided by 7. That means 13. So 3 into 13. A1, N1, and 13 inverse modulo 7. This mi is ni inverse modulo 7. Ni inverse modulo 7, and plus 7 means A2 plus N2 means 7 into 7 inverse modulo 13. Okay, so 13 inverse modulo 7, you just multiply, keep on multiplying this by the elements in Z7. Okay, so 1 into 13, 2 into, so 13 inverse is 6 into 13. If you take 6 into 13, it will give 1 modulo 7. So this 13 inverse is 6 and 7 inverse is 2. So we are getting this value. Okay, you just go through this, how actually we are getting the solution of this system to be 59 modulo 91 product. we can simplify this thing. Essentially, if n1 n2 are co-prime, the pair of congruence n1 n2 are co-prime, the pair of congruences has a unique solution. X is congruent to A modulo n1 n2. Means if these two are also same. Okay, so here I have taken these are a1, a2, ak, n1, n2, nk, and this simplification means it is x is congruent to a modulo n1, x is congruent to same a modulo n2. Then in that case, it has a unique solution. Solution is given by a modulo n1, n2. n1, n2 co-prime, so they are co-prime. So this simplification sometimes helpful. Okay, so I will give you some assignments on this with 3 equations how to get the solution. Means I will set some questions where finding the modular inverse. So you have to find the modular inverse, right? This is 70. So 70 inverse you have to find. 70 inverse modulo 3, 70, 42 inverse modulo 5, 15 inverse modulo 14. If these modulus are very small, you can find the solution very easily. Now I will make it a little bit harder. This I will give large numbers. Okay, and by that time you will learn the extended Euclidean algorithm, and you can apply that extended Euclidean algorithm to find the inverse modulo a large number here. Okay, so you just go through this solution, how actually it is made. Same thing, instead of 2 equations, 3 equations were taken. Okay. Now, we were working modulo n. Now we are interested in Zn star. So the multiplicative group of Zn is Zn star. Zn star is number of elements in Zn which are co-prime to n. The GCD of A, set of all A belongs to Zn, such the GCD of A and n is 1. Okay, in particular, if Zn star, if n is itself prime, then it consists of all the elements 1 to n minus 1. All elements from 1 to n minus 1. So all these elements, if n is prime, then all the elements less than n, excluding 0, all the positive integers less than n, they are co-prime to n. Okay, so this consists of the whole set. Now order of Zn star. Order of Zn star is the number of elements here. So essentially, order of Zn star is how many elements Zn star has, which are less than n and co-prime to n. That is phi n. So order is phi n. And it is closed under multiplication. If you take 2 elements in Zn star, their product is also in Zn star. And we have. Let me state this. This is Euler's theorem. We are going to utilize this. If A is an element for n greater or equal to 2, A is an element of Zn star. If A is an element of Zn star, then A to the power phi n is congruent to 1 modulo n. This is Euler's theorem. This is Euler's theorem. Okay. So this is the generalization of Fermat's little theorem. Fermat's little theorem states that if A is co-prime to n, A is co-prime to n, means it is you take any prime number here. N is any prime number. So if n is any prime number p, then A to the power p minus 1 is congruent to 1 modulo p. That is Fermat's little theorem, and this is the generalized version of Fermat's little theorem. If A and n are co-prime, n is now taken to be composite, and if A and n are co-prime, then A to the power phi n is always gives you 1 modulo n. a to the power phi n, when you reduce this modulo n, you will always get 1. And this thing is important for us, that if n is a product of distinct primes, and if R is congruent to S modulo phi n, then a to the power R is congruent to a to the power S modulo n. So it says that if we are working modulo n, then in power we are working modulo phi n. We will work modulo phi n. Okay, so this modulo, we are working modulo n. The powers means this exponents we are working modulo phi n. Try to prove this by your own. Okay? So this is what we are saying. When working modulo such an n which is product of distinct primes, product of 2 primes maybe. Okay. So when working modulo n such an n, exponents can be reduced modulo phi n. Exponents can be reduced modulo phi n. As I said, a special case of Euler's theorem is Fermat's-Little theorem. It says that suppose P is prime, then Fermat's theorem says that a to the power p minus 1 is congruent to 1 modulo p. P should not divide it. That means A is co-prime to P. A does not have any P as a factor. Okay? A and P are co-prime, then a to the power p minus 1 is congruent to 1 modulo p. So why this particular case? Because if you take this P, in Fermat's in Euler's theorem, if you take this modulus to be a prime number, we know phi of prime number P, phi P is P minus 1. Okay, so you get a particular case when n is prime, this P, A belongs to ZP star, that means A and P are co-prime. In that case, a to the power P minus 1 is congruent to 1 modulo P. Means P need not be in ZP star. P is simply co-prime to N. Means A need not be in ZP star. Okay, means ZP star essentially means the collection of all elements which are less than P and co-prime to P. So all the elements less than P, co-prime to P, essentially there are 5 P elements. That is P minus 1. We are taking A to be any element which is any integer which is co-prime to. So this condition is here, A and P are co-prime. Then in that case, a to the power P minus 1, when it reduced modulo P, you get 1. Also here also the same thing, are congruent, means so when working modulo a prime, exponents can be reduced modulo prime P, exponents can be reduced modulo phi P, that is P minus 1. And in particular, in this, if you multiply both sides by a to the power p is congruent to a modulo p for all integers a. For all integers a. Okay, and a belongs to Zn star. Order of a we define least positive integer such that a to the power t is congruent to 1 modulo n. 1 modulo n. A is any integer in Zn star, then order of a we denote it by this notation, order of a. Sometimes we denote it by order of a. In the suffix of order there is n, order of a modulo n. This is t, this is positive integer t. If a to the power t is congruent to 1 modulo n. So this t should be least positive integer such as this congruence satisfied. A raised to the power t modulo n gives you 1. Okay. By Euler's theorem, we know that a to the power phi n will always be 1 modulo n. Okay, so and t is the least positive integer. T is this order. So order of a modulo n must be less than phi n, and it can be proved that this t is essentially is a divisor of phi n. Okay, so these are all abstract algebra, the part of abstract algebra. If you are familiar with group theory, then you are familiar with all these things. So if the order of a belongs to Zn star is t, and a to the power s is congruent to 1 modulo n, then this t is the least positive integer, right? It is the order. So so that a to the power t congruent to 1 modulo n. So if you have another for s different from t, a to the power s is congruent to 1 modulo n, then t must be less than s, and it is not less than n only. It is essentially a divisor of s. T divides s, and in particular t divides phi n. It comes from the Euler's theorem and applying this result. Now, this one, suppose n is 21. I have taken n to be product of 2 primes, right? 3 into 7. So what are the elements of Z20 star? All the elements less than 21 and co-prime to 21. So 3 and 7 and their multiples will be excluded. So I have to list all the integers which are less than 21 and which does not have 3 and 7 as its factor. So these are the elements. How many elements? It is given by its cardinality is phi 21. If you apply the formula for phi, this is phi 3, phi 7. This is prime, this is prime. So this is p minus 1, this is p minus 1. So 3 minus 1, 7 minus 1, so 12. Okay, so phi 21 is 12, and you can check there are 12 elements in this set. Order of the elements. Okay, so order of the elements. The elements here are 1, 2, 4, 5. List down all these elements here written here, and order is 1. This order is 6. So to find the order, you have to keep on multiplying it by itself, So to take the powers, 2 to square, 2 cube, 2 to the power 4 to the modulo 21, which will give you the 1. Essentially, we know that this means any element you take a to the power 12 is always 1. So 2 to the power 12 is 1, 4 to the power 12 is 1, 5 to the power 12 is 1. Means all these elements to the power 12 is always 1. Because these are elements of Z21 star, and by Euler's theorem, this a to the power phi n, that means 12, is always congruent to 1 modulo n. Order is something which is less than phi n, phi 12, means phi 21, that means 12, less than 12, and it gives you the power some t such that a to the power t gives you 1. Okay, so 2 to the power, you can check 2 to the power 12 is always 1 by Euler's theorem. You don't have to check that thing. This comes from the theorem, or you can check also. But 2 to the power, if you take 2 to the power 6, that also gives you 1. So order is 6. So this is the least positive integer. That 2 to the power 6 gives you 1 modulo 21. Similarly, you can find this, and the order should be the order of this element should be a divisor of 12. So what are the divisors? The possible divisors are 2, 3, 6 and 12. So you have to check 2 to the power all those powers whether it gives you 1. 12 you don't have to check. Before that you have to check which one giving you. So in that way you can check the power, the orders of all these respective elements are there. Okay. Okay. So let us stop here. Okay. So in the next class I will it's already you may be aware of these things. What are primitive elements in Zn star, the generators actually, and what are the properties of generators. All these things we will discuss, and some algorithms. These facts will give me some algorithms. We will discuss those things. Okay. means generator, what we mean by primitive element, under what conditions on this, whether Zn star for all n has a generator or not, primitive element or not, or what are the conditions on this n that restrictions on n for which Zn star has generators. All those things we will discuss in the next class. Okay, let us stop here.